So we learned about overfitting phenomenon. Okay, so this happens because basically this happens because the training data and testing data are different. We are given training data when obtaining the model's parameters. So, but the thing we want to achieve is getting good accuracy for unseen testing data. Okay, so I mean, overly fit our model to given training data may result in this kind of situation. Okay, so we have to design our model. Operate well for other data set than the training data. So we have to make our model be general. Okay. So for that, we learned about the dropout and also the data augmentation technique. Okay, and also I assume you may understand why when training the deep networks, the data have to be very big. So I mean the most the ideal thing might be training the world scale data, which might be the world data means the data we can see from world. Okay, if we can tune, we can make our model to be overfitted to the world data, then it would be the ideal thing. Okay, but it's too big. We cannot collect all, so we can somehow collect some moderate scale data set. Okay, so we normally can deal with this kind of million scale data for training the network. So this million scale data is already very large. So training the deep networks using this million scale data can be, remedy for reduce the generalization issue in practice. Okay, so million scale is already very big, but it's it's far less than the world data, but million scale is kind of the acceptable scale of the data, okay, reflecting the world. Okay, so normally we say for training the deep architecture, we need million scale data. Okay. Okay. And increase the number of data, we can also use this kind of synthetic data using the graphics engine. Yeah, but I'd like to tell more about the assignment now. So maybe I'm assuming that you are starting the assignment one. When doing that, the first thing you have to do is make some data using OpenCV. Okay. This is the first part of the assignment one. Okay. And then I recommend you to store the generated data in your maybe hard drive first. The data scale might be in our preliminary study, we made 50,000 images. Okay. We stored this amount of data in our hard drive, and then we uploaded it in Google Drive, and then mounted it to Colab environment. Okay. So I'm not sure how you guys are dealing with this data in your assignment, but without using this Google Drive, you may have to upload all the data every time you run the model. Okay, so we are actually recommend this method. So you can first upload your generated data, which is in large scale, in your Google Drive. If you have Gmail account, you can get some free amount of free space in the Google Drive, right? So you can upload your generate data in the Google Drive, and then there's a way to mount your Google Drive to your Colab environment. So I will explain that in the code. So actually, this command, I will share that maybe in the Blackboard as well. So these two lines of code is the code for mounting your own Google Drive to your Colab environment. Okay. So if you type this command and click this, yeah, I mean there should be some privacy related message, and you can just click yes to all. Then you can see in your Google Drive, in your Colab environment, this drive directory is generated. Okay. Then in this Drive folder and My Drive folder, your own Google Drive folders are retrieved. Okay. And the path would be /content/drive. Okay. So if you already upload all your data, generated data in the Google Drive, then you can just search for their locations in the Google Drive here and can use that in the Colab. Okay. Are you guys understanding this? Okay. Maybe unless you have to upload all the data every time you want to train in this local drive, that's, taking too much time, okay? So inefficient. So I recommend you to do this. Upload your own data in the Google Drive, and before learning the training code, just execute this code. It takes around less than 1 minute to mount the Google Drive to your own Colab environment, okay? So please do this, okay? If you are using the Colab, then this will be, most efficient way to deal with large scale data, okay? And another tip for the assignment 1 is please do some transfer learning. So what this transfer learning means is we already learned about some famous architectures, famous CNN architectures like the AlexNet, Vision&Learning, or Google LearnNet or ResNet. Okay, we already learned about that. But they are trained by large-scale ImageNet dataset. Okay, they are already pre-trained, and this ImageNet data that have 1,000 classes. Okay, so the difference in their architecture, this might be the AlexNet pre-trained by the ImageNet. Okay, so this is the input, and there are many convolutional layers. And after that, we have to apply the fully connected layers. And the last layer would have 1,000 dimensional vector because there are 1,000 classes in this ImageNet dataset. Okay, but we can somehow, this network, their network parameters are already pre-trained, okay? And it can deal with this kind of large-scale data properly, somehow properly extracting some features in the earlier stage, and then efficiently map the feature extracted to the class probability. Okay, so this ImageNet is this AlexNet was trained for that purpose already. So these earlier layers are maybe helpful for classifying classes in other data set. Are you agree with that? Okay. So maybe if we are dealing with the similar classification task with different data, this already pre-trained weight can be maybe useful for that data set as well, but maybe not optimal. Okay. So what this transfer learning does is we can reuse these earlier layers parameters, which is pre-trained by large-scale data, such as the ImageNet dataset, but we only changes the last layer's dimension because we are assuming that we are dealing with small-scale experiment having the smaller number of classes. Okay. For example, in our case, we are somehow, regressing some, regressing the hours and minutes from the clock images in our assignment one, right? That would be somehow in small scale compared to the ImageNet challenge. So we can just replace the last FC layer to fit to our own application. For example, here, if the small data set is dealing with the C-class classification task, we can replace the last layer to have the C-dimensional vector. Okay. And then we reuse, rather than initializing all the layers using the random weight, we reuse the weight from the ImageNet pre-trained AlexNet. Okay, we can initialize these previous layers with the pre-trained weight and only replace the last layer to fit to our application. Okay, and then for the train, maybe either the last layer only or some of the later layers. Okay, I mean, this is more efficient. In general, training the overall network takes a lot of time, maybe a few days, even using GPU. But if you use this kind of technique, the initialized weights are already very good. So for the convergence, you don't have to spend too much time. Okay, and also if you freeze some of the layers in earlier layers, even the training time would be faster than before. Okay, are you agree with this? Okay. So and also if you follow this link, there are some famous architectures such as the AlexNet, VGGNet, ResNet we learned, and Google LeNet here. And other more recent models are already available in the PyTorch. Okay, so the thing you have to do is just import this, and you can call just models.resnet 18. Then this will have the structure and pre-trained weights of the ResNet. Okay. So actually, for the assignment one, you can use this as well. Okay. And if you make the AlexNet like this, using the same code, you can initialize the AlexNet with the pre-trained with the ImageNet pre-trained weight. So this pre-trained means whether you will initialize the AlexNet randomly or using the ImageNet pre-trained weight. So if you specify this as false, it's meaning that you will not use any pre-trained weight. So your AlexNet will have some randomly initialized weight. Okay, but here we are specifying that as true. So our AlexNet may have the weight which is pre-trained by the ImageNet. Okay, so this net have this AlexNet structure and their individual modules weights are initialized using the pre-trained weight, okay? And if you print out this net, then the result would be like this. It print out each individual modules, okay? Are you guys following this? Okay. But this will have 1,000 dimension at the last layer, right? Okay. So here, what we does is so actually, if you access net.classifier 0, 1 to 6, then you can access this. This is actually that index, okay? So net.classifier, that means classifier and 6th layer. So this indicates this layer, okay, right? Are you guys following this? Okay, and if you want to retrieve, for example, this layer, then you have to type it like net.features, because the name of these layers are features, and retrieve the 7th layer of that, okay? Then that will return this layer, okay? Anyways, the thing we have to do is replace the last layer to have 10 dimension, because our own, we are assuming that here in this slide, we are assuming that our own data set is doing the 10 classification. So that means our final layer have to have 10 dimension, okay? Because we will output 10-dimensional probability vector, okay? So this is actually defining that last layer. It has to be some linear layer that transform this dimensional input to 10-dimensional vector, okay, which would be the probability vector. Okay, so we replace the last layer of the AlexNet by defining this here, right? And this is the code for freezing earlier layers, okay? So for all the network parameters, we will change their required Thunderbird graph as false. This means previous layers, we will not further update their parameters using the gradient descent optimizer. Okay. So this is specifying that we will freeze all the layers, maybe including this, but these are defined after this freezing. So this layer only are trainable, okay? So if you train this network, this net now, then only the last layer would be trained, okay? To fit to your own data. And the first layer's weight are retained from the ImageNet pre-trained weight, okay? So, I mean, this is very efficient way to involve the large scale data, okay? So I'm recommending you to do this kind of thing when doing your own homework as well, okay? But I mean, freezing earlier layers, this depends on you, okay? So maybe training the later part might be helpful for doing your own homework, maybe. Okay, and also this is another tip to save your own model or not. So, I mean, unless without this kind of comment, maybe it takes 1 or 2 days maybe to train your network, or even more to train your network even using GPUs. Okay, so after 2 days, you may get one model variable. Okay, but you have to save it into file, all of its weight into the form of the file, unless when the Colab environment is refreshed, you will lose all the data, all the information you trained for last few days, okay? So this slide is showing how to save and load such model variable. So in PyTorch, you can save your model using this single line of code, okay? And if the model is saved, you can read it by first defining your structure and load weight for each layers using the file here. Okay. So for the loading of the model, you need two lines for initializing your structure and loading the weight. And for saving the model, you only need one line of code. Okay. Okay. So are you guys following this? Okay. So this is some tip for the assignment one. Okay. Maybe the assignment one, we can give you maybe 1 or 2 weeks more. Maybe, yeah, we may extend this deadline. Approaching the deadline. Okay, so please don't give up. Okay, and please complete it. Okay. Okay. And now we will learn about something about the learning rate. Okay, so this learning rate is something we saw here. So previously, the gradient descent algorithm that looks like this. Okay, so and this epsilon that is called as the learning rate. Okay. So we multiply, this is the direction where to update this sector, okay? And we multiply very small scale of the number to that direction and update the parameter, okay? That's the gradient descent update. But properly set, this learning rate is also very important, okay? When during the training. And also the most also important thing is the running rate. It is also important, but more important thing is this DL dissector is not that stable actually. Okay, so this is the standard gradient descent or stochastic gradient descent rule. I mean, we normally show you some graphs like this. The loss function or the error of the network according to the sector, the parameter of the model, we normally draw it like this, okay? If the loss function that's, looks like that, if that looks like this, it's the ideal case actually. So if your parameters are at this point, then you can get the slope to reduce the loss L, okay? And it would be, it would reach this optimal, the global minimum point easily using this update, okay? This is kind of the ideal case, but in the reality, the data is not that clean. Our real data sets that's not that clean enough. So mostly the error functions according to the parameters are very complex like this, okay? So if it looks like this, for example, there's some issue when using this simple gradient descent update. So let's say your parameters initialized sector was here. Okay, you may randomly initialize your parameter sector, and let's say we randomly initialize it to be here. Okay, and then it will reach this point, it will reach this point, using this simple gradient descent object. Okay, when it reaches this point, that dl dissector goes to 0 because their slope in this kind of point immediately goes to 0. Are you agree with that? Okay. So this is the point. Also, this is the point. This 4 point, their dl dissector is exactly 0. Okay. So, I mean, this may cause your network to be, I mean, stuck in the local minima. So this kind of points are called as the local minima, and this is the only global minima. Okay. So this is usually called as local minima. This is local minima. And this is the globally minimum point. So there is only one global minima, but there could be several or many local minima in your loss function. Okay. If your parameters are stuck in this point, this local minima, then it's not. It could be not bad. It could be not bad, but it is not optimal. Okay. So I mean, your sector, the model's parameter have to stop here. Okay. But if your parameters are stop here, then it would not be that bad, but it's not that optimal. Okay. So the best parameter might be here. Okay. So for reducing this phenomenon that stops gradient update in the local minima, we may use the concept of momentum. Okay, momentum. So that's here. That is explained here. So this is the previous rule, but we have another term M here. Okay. So what it does is the concept is like this. So here until here to here, we update our parameters because the DL dissector might be not 0. Okay, but in this point, exactly this local minimum point, the DL dissector may approaching to 0. So the update will be stopped here. Okay, that's the problem. To avoid this, what we propose is we will use this concept of momentum. So I mean, here until here, the DLG sector becomes approaching the 0, but actually there are some velocities are remained. Okay, how to say? Let's say this is some person. I mean, assume this looks like a person. Okay, somehow we are reducing our acceleration. Okay, how to say? I mean, maybe you already know about some physics, right? There are some velocity and acceleration when describing the motion of the object. Okay, this situation is similar to that, and actually the momentum itself is the term used in the classical physics. Okay, so I mean the DL dissector approaching DLD sector to 0 is similar to reducing the acceleration when approaching this point. Okay, but at this point, even in this point, whose acceleration is 0, there is some of the velocity. Okay, so even the acceleration 0 at this point, but there are some velocities. So what they do here is they have to update weight. Maybe previously it would be this, okay? Maybe, sorry. Maybe I will use the same notation here. Previously, the parameter was sector, but here it is V and U. So I will use the same notation here. So we have to update previous times parameter, but we somehow will reuse our current times velocity when updating, when calculating the directions of this vector. Previously, we only used DL sector for this part, but now we will also use our velocities and their here notations are quite dirty. Sorry about that. So are you guys understanding this? So previously there's only this term when multiplied by this epsilon, but now we will somehow use sector itself when updating, but we may multiply some weight to current velocities and update it when updating the sector old, okay? So this is the old, okay? So this is the new formula for updating the parameter sector, okay? So this is actually meaning some velocity. So the DL sector, it goes to 0 at this local minimum, but this term is not exactly 0. So it will give some values actually, okay? And if we simplify this, then this mu is multiplied with epsilon and can be added with the original sector here. So that is actually same as multiplying m to the original value. Okay. Sorry. Sorry, I explained everything. So sorry about that. So this is not exactly sector. So this is our parameter sector, but we have another term, which is the velocity here. Sorry about that. I also understood that here. So previously our term was this one, okay? But now the thing would be sector new is updated by some velocity, some how to say, let's say it's V, okay? And also we update this V using the two terms, okay? I mean, multiply M minus DLD, how to say, this is sector, okay? So previously, this term was only constituted with this dl dissector, okay? But now it is constituted with this kind of velocity term, okay? Okay, and this velocity term was initially zero, only accumulating this dl dissector, okay? But when it approaches exactly zero at this point, local minima, this velocity term would not be exactly zero. Okay, so that's why even at this point, it has some momentum to climb up this small hill. Okay, so these points are slightly higher than this point. Okay, so using this gradient term, you can somehow have some ability to climb up this and avoid this local minima having very small hill. Okay, but when you approach here, you also have some momentum. So you may climb up until here, but your velocity will be zero at this point, and it only has a slight slope here. And also, somehow this is converged to this global minima by climbing up these small hills. Okay. So are you guys understanding this? Okay, sorry about the, this V is not same as sector, okay? We have to define another term that is kind of the accumulation of previous DL sector. We have to define this separately and have to update parameters using this new term, okay? So thanks to this term, you can climb up the small hills in the loss functions, okay? Are you guys understanding this? Okay. This Nesterov, that's similar, but slightly improved compared to this momentum things. So this is the same term as before. We will now update our parameter W and B with this velocity term. And that velocity term is constituted with dl dissector with the multiplication of some value. This m would have to be in between 0 to 0.9. Anyways, they weight decay the original term and add this new term, okay, to get the new velocity. Okay, that's what be here. So that's actually using the momentum concept. But in the Nesterov gradient descent, what they say is previously this dl dissector was also when calculating this dissector was the old parameters. Okay, this was also the old parameter. We differentiate error only with Wt or B of t. The previous parameters which exist before the update. But what Nesterov gradient descent say is we have to count the new direction, new parameters. This is the parameter, which is updated with the momentum, okay? So we have to get the gradient using these new terms, okay? That's what this Nesterov gradient descent is saying. So by calculating the gradient using these updated parameters, we can get more accurate directions to update the parameters. So, there's very small change compared to the momentum, original momentum. Previously, this term is calculated using the original parameter, but here they say we have to get this DL, this sector, by changing this sector to be updated. Okay, so it provides, more accurate directions to update. Okay, that's the Nesterov gradient descent. Okay, and next thing is the learning rate. Okay, so considering this learning rate, there are new schemes proposed, such as the ADA-GRAD and RMS probe and ADAM. So you have to understand this kind of optimizer, you have to understand learning rate. Okay, more in detail. So I will explain this. So we already know that this epsilon was the learning rate. We already know about that. Okay. If you set this learning rate too high or too low, the network parameter update may have some issues. Okay, so if the learning rate epsilon is too big, let's say if you set this as the 100 instead of the very small scale value, then at this point, you may get the optimal direction, DLD sector. You can calculate that. But actually, you will update. Your direction is okay, but if you set epsilon too high, then your next parameter would be located at this point. Because this point, this value was too large, then your parameter sector would be changed into some location which is far different from your current location. Okay, are you agree with that? Okay. And then also here you calculate the LD sector again, but because your epsilon is too high, the model will be again too much varied from the current location. Okay, and this this happens, and the training have to converge like this, but it diverges. This makes it diverge like this. Okay, and if learning rate is too high, then your model, the optimal model, cannot be found. Actually during the training. Okay, so normally we have to set our epsilon value small in scale. Okay, are you guys following this? Okay, but if you set the epsilon too small, the problem is the update, their scale might be very small. Okay, their one step update will be very small, and it may take too much time to make the model convergent. Okay, so because of that, we have to set this epsilon value properly. Okay, in between these too high or too small values. Okay, you can feel that during training. At the early stage of the training, if you see some loss function, this is actually the loss function, and it changes a lot in early stage of the training, then it indicates the learning rate could be too high. Okay, so you can reduce, you can multiply maybe 0.1 to the learning rate and see the loss function is becoming smoother. Okay, so that's actually the way to tune your learning rate. Okay, so you can start from the big values as much as possible and see the loss function and see whether it is fluctuated or not during each epoch. And if it too much fluctuated, it indicates that it's too high. So you can multiply 0.1 to that until it shows some smooth changes. Okay, then it can avoid too small values and too high values. Okay. So that's the thing about the learning rate. So if the learning rate is too high, the loss will not converge, and it would be actually diverge. Okay. And if you use good learning rate, the learning curve would be like this. Okay. And if you high learning rate, it would not be converged. It could be trained with moderate high learning rate, but it could not, manage it to have the detailed parameters. Okay, and low, if you set it have the low learning rate, it would have, in this time, with this epoch, it could be reduced further, but it may take very large amount of time to make your model converge. So, setting this learning rate would be, very subtle things during the training. And also, actually, there's some learning rate scheduling schemes in PyTorch. So there are some implementation, but this is not that complex. Okay, what they do is basically they have the high, but kind of moderately high learning rate at the early epoch. Okay, but later they gradually reduce learning rate at several epochs. Okay, so their scheduler is doing, actually reducing the learning rate after several epochs. So that's what this torch.optim.learning rate scheduler are doing. So there are actually two learning rate scheduler, two frequently used learning rate scheduler. So one is the step learning rate scheduler, and the other one is exponential learning rate scheduler. So what they does is, here you can see in this code, well, we can use this exponential learning rate scheduler, and we can give our optimizer defined here and set gamma values here. This is actually the hyperparameter for this exponential learning rate scheduler. And here you can visualize which kind of learning rate it would have here. So it gradually, the initial value would be this, and it gradually reduced the learning rate. So, and the way it reduced the learning rate would be the exponential. Using the exponential function, it reduced the learning rate. So that's why this is called as the exponential learning rate scheduler. Okay. And here there are another learning rate scheduler, which is the step learning rate scheduler. And if you plot their learning rate scheduled, then they are somehow looks like this. Okay, so the learning rate, the difference of the learning rate are somehow same offset. They have some, as far as I know, they have some same offset between this learning rate. So that's why they are called as step learning rate scheduler. Okay. And you can also change this step size, okay, and can get the different values here. So if you specify step size, then it would change the learning rate in this manner. So this would span maybe 2 or 3 epochs to reduce the and these are also say similar and reduced and retain the same learning rate. And actually, yeah, it looks like this kind of patterns. Okay, this is the learning rate scheduler. Okay, so you can actually use this learning rate scheduler during the assignment 1. But I mean, yeah, I mean the simple scheme might be okay for fulfilling your assignment 1. Okay, so even using even without using this scheduler, maybe for the assignment 1, it would be converged easily. But you can also use this learning rate scheduler. Okay, and the next topic would be ADA-grad. Okay, so previously in our optimizer, we applied same learning rate for all the parameters. So sector actually means all parameters here. Okay, this sector was the all parameters, and we update all parameters using their individual DLD sector. Okay, and the epsilon was the constant before. The epsilon was same across all the parameters before, but this other grad means they try to have different learning rate for individual parameters. So adaptively update gradient for individual parameters. That's the idea of ADA-grad. Okay, so it updates parameters with a large step whose parameters haven't been changed a lot. Okay, so DL dissector could be varied for each individual parameter. So for some parameters, DL dissector could be large, and for some parameters, DL dissector was relatively small. Okay, so this is saying that for the parameters whose DL dissector was relatively high at the later epochs, they would update it. I mean, no more updated. Okay, but if the DL dissector for some parameters was small in early epochs, then it is saying that they will update them more in the later epochs. Are you guys agree with that? I mean, following this? So, I mean, this is more adaptive parameter, can provide more adaptive parameter update. So this is the standard gradient descent. G is actually meaning this, okay? This other grad is meaning they have additional R array for each parameters. These R have to be prepared for each parameter. And we somehow accumulate their DL dissectors square value. Actually, this is that to this R. Okay. Initially, it was 0, but they are added with the current epochs DL dissector, and they are actually accumulating it. Then this may have some information that which parameters are updated across epochs. Okay. So for the parameters whose DL dissector was high at early stages, this R may have higher values than others. Okay, and for the parameters whose DL dissector was relatively small, then R would be maybe small in scale. Okay, I agree with that. So this R is having which parameters are updated in early layers. And actually, this is the learning rate. This is the constant same as the small value we set. Okay, and this is newly introduced value. So if R is large, it indicates that there was large update for that specific parameter. So the learning rate have to be inverse of that. Okay. And if R is small, then it means in earlier stage, that parameter was updated not much. So the learning rate for that parameter have to be large. Okay. And I mean, if R is 0, what happens? If we constitute this term only with this, then if R is 0, then it goes to infinity. Okay. So to avoid that, we add this small delta value. Okay. So this is the only difference compared to the SGD. Okay. So this term was added, and this R is obtained for each individual parameters. Okay. They are actually accumulate the square of the gradient for each epoch. And it is indicating that which parameters are updated much in earlier layers. Okay. And we will update them less in the later layers. That's the ADA graph. Okay. And next is RMS group. The ADA graph, it also has some problem. Actually, it looks like optimal, but there's already there is still have some weaknesses. Okay, are you guys? Is there anybody who knows that? No, maybe it's not that easy, actually. But is there anybody who can? Okay, maybe not. Okay, the thing is, this R value continuously become large. If the epoch goes, this R continuously we will go to have will have the large value. Okay, so at some after some epochs, this term goes close to zero for most of the parameters. Okay, so there's some scale issue. How to control the scale of the R, because as epoch goes, this value close to zero, and there would be no more update for those parameters. Okay. So actually, there's some uncertainty that how to say. I mean, let's say there could be this kind of situation. So let's say there are 100 epoch trading. For that individual sector, I mean, for 1 to 3 epoch, their DLD sector, let's say the y-axis is denoting the DLD sector. Let's say 1 to earlier epochs, that parameter could have large DLD sector, right? Because they are accumulating DLD sector for R. They are accumulate relatively lower learning rate after this earlier epochs. Indeed, we can say it is DLD sector for later epochs could have lower value, but after some epochs, it could also again have this kind of higher DLD sector, because I mean there could be some situation like this. Okay, so even in later epochs, for that specific parameters, we could update more. Maybe there could be situations like this, but in general, this is rare. But there could be some situation like this. But even for this situation, this learning rate for these specific parameters are already goes to zero, because as epochs go, this learning rate is converging to 0. So this may make some trouble because even though they have higher DL dissector at the later epochs, there could be no update for that specific parameters anymore. So there's some scale issue of that in the R variable that as epochs go, it continuously increased and never decreased. So their learning rate always goes 0 and never be larger than 0 again. That's the problem. So in RMS Pro, what they suggest is previously they update the R using scale of gradient, but here they have some weighting scheme like this. So their sum of weight is always 1, right? This is always 1, okay? So they multiply 0.9, for example, to original R. And if this is 0.9, then this would be 0.1 to the new values, okay? So somehow these values are, previous R was not bounded, but now these values are relatively bounded. We can control their scales, okay? So this RMS probe provides more stable features than the other graph. Others are same as the other graph, but only this updating scheme is improved in RMS probe, okay? And anyways, because of this, they can solve some scale issues. And the next thing is the Adam optimizer. It somehow combines the learning rate issues. This was dealt with ADA-GRAD and RMS probe. Okay, and direction was solved by momentum and Nesterov gradient descent algorithm. So somehow Adam is combining these two approaches. Okay, so they combine RMS probe with the momentum concept. That's the Adam optimizer. So somehow these R, they have the R which which accumulate the scale of the gradient to adjust the learning rate. And also this S is accumulating gradient with some momentum. This is momentum term. So we have to have some, velocity and accumulate this gradient value. And this is kind of S is indicating the velocity. So, and also we normalize it properly. And this is the new term for Adam. So similar to RMS Pro, we have this term that normalize the learning rate. And this is the DL dissector term with some momentum, okay? So this S is the accumulation of gradient considering the velocity, and they are normalized, okay? This is the term considering the momentum, and this is the term considering the adaptive learning rate, okay? So this is the new optimizer, which is called as the Adam, okay? So relatively, the standard gradient descent algorithm that update the parameters using this simple term, this have more features, okay, considering the learning rate and considering the momentum, okay. But thing is, in the code, the PyTorch already implemented all the optimizers, okay. The thing you have to manage in your code is replacing this SGD to Adam, okay. It's very easy, right? And you have to specify some of the hyperparameter, okay, which is epsilon and delta, and some of the hyperparameters are these values, the beta 1 and beta 2. Okay. So actually, this is beta 1 and beta 2, and epsilon, and yeah, this is epsilon, and this would be delta. Okay. So, I mean, when using the PyTorch, this is very simple. Okay, you can just replace your optimizer with Adam instead of the SGD. So, I mean, most of the recent CNNs are trained by the Adam, but in many experiments we also use the SGD. But in practice, it converges well. But Adam is providing actually in general, provide the best solution. So I recommend you to use this Adam in your assignment. Okay. Actually, this RMS probe, AdaGrad, other optimizers are also implemented in the PyTorch. So using how to tune their hyperparameters in the manual, you can, involve their, different optimizers in your training in the code, okay, by replacing code like this. So let's finish here for today's class, and maybe we can meet again 28th of the October, which is the Monday, 2 weeks later, okay, after the midterm. Okay, see you guys. Bye. Thank you.